Alrighty. In this video, we are going to be talking about the definition of the definite integral, which requires limits. So just like how we had the definition of the derivative using limits, we're also going to have the definition of the definite integrals using limits. And we're also going to be using summations. And we're going to get to that on why we use summations in like 2 seconds. But I want you guys to think back about when we did 1/4 x squared and we only did 6 subintervals from 0 to 6. So we only did 1 sub. But what if we used 10 subintervals instead of 6, or maybe 100, or maybe even 1,000, and seeing how that would work? So let's pretend that we have our little graph right here of 1/4 x squared, right? And this is from 0 to 6. So what we did is basically this right here. 1, 2, 3, 4, 5, 6. Okay, yeah, something like that. But what if we used more than that? So let's say that I have a rectangle right here, 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 and so forth, and then added them. Maybe even here, 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 here. Essentially, if you add infinitely many rectangles, it's going to cover up the area under the curve of what you're trying to find, which is why we are going to be using summations here, because we're going to add up each individual tiny piece of that area under the curve. So the definition of a definite integral is if f is a continuous function defined on a to b, and if a to b is divided into n equal subintervals of width delta x is equal to b minus a over n, and if x sub k is the right endpoint of subinterval k, then the definite integral of f from a to b is this lovely thing right here. So what is this saying? Let's pretend that I have a graph right here, and we want to find the area under the curve of this graph right here. Let's say that this is from A to B. The width of each rectangle is going to be delta x is equal to b minus a over n, where n represents my subinterval. So here, delta x would represent each width of my subinterval of this little thing right here. So this is like this tiny piece right here. We're going to find the right endpoints of each rectangle by adding a. So this is going to be x sub k. That's going to be a plus k times delta x. So delta x represents my width. My k value right here just represents my subinterval. It's basically representing the point right here, the right endpoint. And then to find the area of the kth rectangle, we have f of x sub k, which is going to be my height. So we have f x sub k, my height. So this is going to be this thing right here, times delta x, which is my width. So the area is this thing right here of one rectangle. So this is going to be my height, and then this is going to be my width. We're going to use some summation notation from 1 to n to get a right Riemann sum approximation. So that's going to give me the limit as n approaches infinity of summation from 1 to n of my area, because we're just adding all of the areas up at this point. So we're adding this up, this up, this up, this, and so forth. So that's what the last statement represents, which is what we're essentially trying to find. there in green. Okay, so for 1 through 3, what we're going to do is write each integral using limit notation. And then in another video, I'm going to talk about how to evaluate using summations, which is just a fun bonus part. So the first thing that we're going to do is find the width of each rectangle from A to B. In this case, if I were to visually draw this out, I'm going to have this right here, 4x. We're going to pretend that's 4x. Now, obviously, you could find the area of this using geometry and trapezoids. So let's say that this is 1, so that's 4. 5 is 20 right here. So this is 1 to 5. So to find the width, I am going to have delta x is equal to 5 minus 1 over n, where n is going to represent how many subintervals I want. So I have 4 over n. Now the right endpoint, it's just going to be my a value, so where I'm starting. So that's going to be 1 plus k. And then we have my delta x, my interval, or 4 over n. I'm going to rewrite that so that it's pretty, so that it looks like 4k over n. That's going to be x sub k. Okay, so we are now ready to plug this into my summation limit. So I have the limit as n approaches infinity of the summation of k to 1 from n. And then notice how here we have f of x sub k. So f is going to be your function, whatever function that is. So instead of x, I am not going to use x, but I'm going to use what I found with x sub k. And that's going to be 1 plus 4k over n. So substitute x with x sub k. So that's going to be f of x sub k times delta x, aka my width, which is going to be 4 over n of each rectangle. Now, you don't need to really simplify this. If you want, you can. We will simplify this later on whenever we get into the when we get to evaluating this using limit notation. Like I said, you can obviously find the area using trapezoid and the area of that. But since this lesson is mainly focusing on the formal definition of the integral, we are going to be using summations and limits. Okay, number 2, we have the integral from 0 to 2, x squared plus 10 dx. So if I were to draw that out from 0 to 2, it might look something like that. So we want to find the area of this right here. The first thing that I'm going to do is find delta x, which is going to be my width of each rectangle. That's going to be 2 minus 0 over n, which is going to be 2 over n. My right endpoint is going to be whatever my a value is, and then I'm going to add my delta x times k. So that's going to be x sub k. Then I'm going to write the limit as n approaches infinity of my summation of k to 1 to n. And then my function. Remember that this is going to be f of x sub k, which is this whole thing right here. So we have x squared, but instead of an x, I'm going to write 2k over n squared plus 10. Not really doing anything with the plus 10 because I can't really substitute in, but remember that this is a function. So because it's a function and 10's a constant, I'm just going to leave 10 right here. So this is going to be f of x sub k times your delta x, which is going to be 2 over n. All right, same thing for number 3, but I'm not going to draw it out because hopefully you look at this and just see what's happening here. Delta x is going to be 3 minus 0 over n, or 3 over n. X sub k is going to be 0 because that's your a value, plus 3 over n times k. So that's x sub k. Then we have the limit as n approaches infinity of the summation from k is equal to 1 to n, and then f of x sub k. In this case, we're going to have 2 variables that we're going to substitute in. So we're going to have 5, 3k over n squared, minus 2, 3k over n, and that's going to be f of x sub k. And then we have my width, which is just going to be 3 over n. Okay. Same process with number 4. Even though we have a sign, same thing. So the delta x is my width, so that's going to be x. Delta x is equal to pi minus 0 over n, which is just pi over n. X sub k is going to be 0 plus pi over n times k. Then we have the limit as n approaches infinity of my summation from 1 to n of f sub k. So in this case, sine of pi k over n. So that's going to be my f of x sub k. And then we have my delta x, which is just going to be pi over n. There you go. So, what if we're given the Riemann sum and we want to turn it back into a definite integral? So looking at number 5 right here, we have the limit, and we have a couple of things that we notice. We have 3k over n squared minus 1, and then 3 over n. Well, this thing right here at the end will always represent my change, my delta x. So my delta x is going to be 3 over n. Now, to figure out what your a value is, we're going to see our substitution first. Yeah, let's actually do that first. Let's figure out what f of x is based off of my substitution. So notice how here, if delta x is 3 over n, then I'm going to have 3k over n squared minus 1. So my substitution here is going to be 3x squared minus 1. Okay? We still need to figure out what a is and what b is, but we know that it has to be a difference of 3. And remember, to find my a value, x sub k is going to be equal to a plus delta k times delta x. Well, my delta x is 3 over n. We have k. There's nothing that we need to add, so in this case, a is going to be 0. Since a is going to be 0, I have 0 to 3. So my definite integral is from 0 to 3, 3x squared minus 1, and then be sure that you have a dx. All right, we have number 6. We're going to do the same thing here. So I'm going to find delta x. That's going to be the easiest. That's going to be 5 over n. I'm going to look at f of x, aka what substitution's happening. So with number 6 here, I'm I have this substitution that's going on, so I know that f of x is going to be 5x cubed minus 1. So now I have my integral from something to something, but I know that it has to be a difference of 5, and then 5x cubed minus 1 dx. Well, notice how here my x sub k is 5k over n minus 2. And remember that x sub k is a plus k times delta x, which is this thing right here, which means that my a value is whatever your constant is. In this case, my a value is going to be negative 2. Now, because my difference is 5 right here, this tells me that my b value has to be 3, so that whenever I do b minus a, I'm going to get 3 minus negative 2, which is 5. So now I have my integral from negative 2 to 3 of 5x cubed minus 1 dx. Same thing with number 7 and number 8. I'm going to do 7, and then you guys can do 8 on your own, and then, you know, have fun with it. So for 7, we have delta x being 3 over n. F of x, it's going to be a sine function, so just sine of x, since there's nothing else. Okay, we have x sub k being 5 plus 3k over n. I know that delta x times k is 3k over n, which means that my a value has to be 5. So right now I have my integral from 5 to something of sine x dx. Now, my difference is going to be a 3. So now I need to think b minus 5 is equal to 3, which means that my b value has to be 8. So my integral is going to be from 5 to 8 sine x dx. Okay, and then I'll let you guys do the last one. That is going to be from 0 to pi over 6 sine x dx. Check your work there. And then whenever we are in class, we'll do more practice on this, and then we'll also do more practice on properties of integrals.